Welcome back to another episode of Science with Surbeck. Today what we're going to be talking about is physical and chemical properties, and then also units of measurement used in the chemistry lab. Before we get going, I want to outline a couple of objectives that you should be able to accomplish by the end of this lesson. Number one, distinguish between physical and chemical properties and also between simple physical and chemical changes. And objective number two is you should be able to list the basic SI and metric units and the commonly used prefixes in scientific measurements. So let's go ahead and get started here. So the first thing, before we even get into physical and chemical properties, I want you to know that each substance has a unique set of physical and chemical properties. And so this is what distinguishes each and every substance that we deal with. Having these different properties allows us to separate them, allows us to classify these particular substances into different categories. So we start out here with physical properties. And physical properties are measured without changing the substance. So some physical properties include things such as color, density, odor or smell, melting point, boiling point, and hardness. Now, these 6 examples are just a few examples of physical properties of substances. They can range in a multitude more. But again, this gives us a few examples to base ourselves what physical properties are. So now what we have down below here is chemical properties. And chemical properties are going to describe how substances react or change to form different substances. So one example of a chemical property is flammability, or the ability of a substance to burn in the presence of oxygen. So now that we've described both physical and chemical properties and have a few examples of each of these things, we can get into a little bit more details about these properties and how we can use to distinguish between different types of substance. So what we'll do here, we'll transition to our different categories of properties. And so there are 2 properties or 2 categories of properties that we are going to be dealing with in this class. And so this first category of property is known as an intensive property. And an intensive property does not depend on the amount of substance that is actually present. So some examples of intensive properties would be something like temperature or melting point. No matter how much of that substance we have, these things, these values or these properties are always going to be the same. So take, for instance, ice. Ice, pure water that's frozen, is always going to melt at 0 degrees Celsius under standard conditions. And that is something that it doesn't matter if we have a whole bag of ice or we just have 1 ice cube. Again, it doesn't matter how much we have of that stuff. It matters what it is, and that property will remain the same no matter how much we have. Our other thing with intensive properties is what it does is it gives us an idea of the composition of a substance. And so what this does is it is used to identify one particular substance. So again, if we go back to that melting point example, if I have 2 solid substances and I'm identifying their melting point and I know they're different or I'm trying to distinguish they're different, if they have different melting points, I know that I am going to have 2 different substances. So our other property that we need to be concerned about here is an extensive property. And an extensive property, unlike the other property above here, it does depend on the quantity of the substance present. And some examples of extensive properties include things such as mass or volume. And so the whole purpose behind an extensive property is to give an identification of the quantity of substance present. So again, just to recap this, an intensive property does not depend on how much we have of that substance, but an extensive property does depend on how much we actually have of that substance. So that now that we've identified these two categories of property, we can go further into detail into physical and chemical change. So we'll transition here, and the first thing I want you to know is that physical change occurs when substances change physical appearance without altering its identity. So a good way to think about physical change is that if we have a physical change occur, we're going to have the same substance before and after the change. So a really good example of a physical change is changes of states of matter. So one example of a change in a state of matter would be liquid water evaporating into a gas. Another example would be liquid water freezing. Both before and after evaporating and freezing of water, we still have the same substance, water, H2O. However, the state of matter has changed, and that is a physical change because we've altered that physical property of water. Now, on the flip side, chemical changes occur when substances transform into a chemically different substance. And this is more easily thought of as a chemical reaction. And so a really good example of this is when one substance undergoes an identity change. So a real-world example of this is a reaction between hydrogen and oxygen gases to produce water. When this reaction occurs between hydrogen H2 and oxygen O2, you can see that when we get the resultant of this reaction, we have a totally different substance just by looking at the components involved in that substance. H2O has a different composition than either hydrogen or oxygen alone. So now that we have physical and chemical changes in mind, I want to go through a couple examples down here that help us distinguish between each of these types of changes. So we start out here with plants making sugar, which sugar is C6H12O6 from CO2 and H2O. Now in biology, they commonly call this process the photosynthesis process to be able to do that. And so because sugar, C6H12O6, is a different substance than CO2 and H2O, we can classify this as a chemical change. Now, water vapor and air forms frost. So let's say you go out on one of a chilly October, November morning and your car outside has frost on it. So ask yourself, that frost is water and it came from water vapor. So did this change from water vapor to solid water, frost on your car, did it ever change its composition of H2O? The question or the answer to that is no. The water is still H2O. It just went from a gaseous form to a solid form. So this second point down here is a physical change. Now, melting gold. You go out west and you find some gold and you melt it down. So we started out with solid gold and we heated it up to get liquid gold. So does gold Does it change at all chemically? Again, the answer is no. We've just changed the state of matter. So melting gold is also a physical change. Okay, so now that we have identified some differences in chemical and physical change, again, physical is not going to alter the substance at all, and then chemical change is going to transform it into a different substance. So just to clarify, physical is going to change without altering those physical appearance. So now we can identify, now that we have some ideas behind changes, we can get into what we can actually do with these particular things that we know, and that is separate mixtures. So most things don't often come as a pure substance in the world, and so what we have to do to obtain that pure substance is we have to separate the mixture into its individual parts. And so how we separate mixtures is by using different separation techniques to exploit differences in properties, both chemically and physically, of the components of the mixture. Now, if we're wanting to separate each component out and then analyze that substance, we need to separate via physical means, because if we separate via chemical means, we will have a different substance, and therefore we can't measure something like the mass at the end of the separation technique. So oftentimes our separation techniques to obtain that identity of those components are going to be by physical means. So I'm going to go over 3 common separation methods. Some we will use throughout the year in the lab. So the first common separation method is filtration. Now, filtration removes solids from liquids. So a good example of filtration would be removing a salt and sand mixture by filtering out with filter paper and a funnel, filtering out the sand from the salt. And usually you have to mix it with water so that salt is dissolved in the water and the sand is not. Another common separation technique is distillation. And so what happens with distillation is that we are going to boil off one or more component of the mixture. And so distillation is going to depend on the different abilities of substances to form gas. And so real simply put here, this last point is that different substances are going to have different boiling points. And so as one liquid in that particular mixture reaches its boiling point, it will evaporate into a gas form, and then you could cool it to form or just get that particular part of the mixture. Now the third separation technique is chromatography. And what happens with chromatography is that it is going to exploit differing abilities of a substance to adhere to the surface of solids. And so chromatography is based on the differences in polarity of different substances. Okay, so we have identified physical and chemical properties. We've identified intensive and extensive properties. And then we've also identified those changes that can occur with a substance, and we've gone through some different separation techniques. So what we're going to do now, we're going to transfer to how we can better acquire data in the lab environment. So what we're going to do here is we are going to transfer to what type of measurements that we use in the lab for chemistry. So with measurements in the lab, there are many properties of matter that are quantitative. And so what we have to remember is that quantitative data is associated with numbers. And so that means to get a quantitative data, we're going to have to make some measurement. And for our measurements in chemistry class, they're going to involve two simple things. One of these things is a number. So that number is as simple as something that is read off of an instrument. The other thing that is very important for us to associate this with a property or with data is a unit. So a unit is just as important as the measured quantity, because without it we have no idea what we are meaning or what the basis of that measured data is. So in science, what we use is the metric system, which the metric system are a series of units that are most often used for scientific measurement. There's very few exceptions. And this metric system was developed in France in the late 18th century. And so that brings us to our next phase here, and that is talking about more specifically the SI units, or how we like to call it is the System International de Units. Again, it's easier for me and you to say SI units. But the first thing here is that the SI units stands for System International de Units. Again, it was French, and it was first established in that 18th century. And so the SI units in the 1960s were actually agreed upon by the international community as a unit that would be used for scientific measurement. And so what that did is, by making an international set of units, all scientists across the world could communicate more easily with results they obtain in lab experiments. So there are 7 SI base units, a handful that we don't get to in this class, but I do want to go over them. So for mass, the SI unit is the kilogram. And I am going to put the abbreviation for that unit in parentheses. The SI unit for length is the meter. For time, the SI unit is the second. And temperature, the SI unit is Kelvin. And the amount of substance present, the SI unit is the mole. And the last two we won't use as often, but for the electric current, the SI unit is the ampere. And for luminosity intensity, the SI unit is the candela. Now, there are some times when these base units are not big enough or are too big. So what we need to do is, even though we have these as our base units, we need some way to modify it to make it more applicable to the particular measurements that we are taking. So what we do is we use prefixes, and these are used to indicate smaller and larger units obtained by decimal fractions or multiples of the base units. So an example here is the prefix milli. Now, milli represents 1 times 10 to the negative third, or 1,000th of a unit. So a milligram would be 1 times 10 to the negative third of a gram. So to help you out and understand the prefixes and what they are in accordance with the base unit, what I have attached here to notes are the prefixes chart, and this is something that you need to memorize. So you need to be able to know, for example, that a kilo unit is 1 times 10 to the third of a base unit. And what's really helpful here, the examples in this chart are going over watts, but you can tell what one of these either large or small units is equal to in accordance with that base unit. So again, it really helps you out to understand what exactly our equivalents are. So when we go to do some dimensional analysis or some problems, you have this in front of you. Again, this is something that does need to be memorized. You can use it throughout your homework and your online problems, but it does need to be memorized. So now what we can shift gears is how exactly we go through and we make some measurements in this particular class. Okay, so all of these units that you see here are measurements that occur just from the base units. And so a measurement that we use for length for a base unit is a meter. And now a meter is the SI unit for length. And just to familiarize yourself with what a meter is, 1 meter is equal to 1.0936 yards. And so we move down to mass. So for our mass, a kilogram is the SI base unit of mass, not weight. Now just to give you an idea about a kilogram is equal to about 2.2 pounds, or pretty typical of the average textbook. Now for temperature, we're going to get into a little bit more detail, but temperature is the measure of hotness or coldness of an object. And so a couple of things that we need to know about temperature is this. Number one, it's a physical property that determines the direction of heat flow. And we also need to know that heat flows spontaneously from a substance of higher temperature to one at lower temperatures. And again, I kind of squeezed that in, but it says heat flows spontaneously from a substance of higher temp to one at lower temp. Now, in science, we use 2 scales to measure our temperature. The first of which is the Celsius scale. And now in the Celsius scale, water is going to freeze at 0 degrees Celsius and boils at 100 degrees Celsius. And this is at sea level or 1 atmosphere of pressure. Again, that freezing boiling temperature is dependent upon your external pressure. Now we also use Kelvin. And Kelvin, as mentioned before, is the SI unit for temperature. And so for Kelvin, water is going to freeze at 273.15 Kelvin and boil at 373.15 Kelvin. Again, at sea level or under 1 atmosphere of pressure. So notice how the difference between freezing and boiling is both 100, or a unit, a measurement of 100. And that's because both Celsius and Kelvin, they use the same scale. The starting points for the freezing is different. And that's because a Kelvin is going to factor in absolute 0. Now, another thing to note about the unit of Kelvin is that it is based on the properties of gases, which we'll later call the kinetic molecular theory. Again, that last part here, I squeezed it in, but that is the kinetic molecular theory. Now, Fahrenheit. Fahrenheit, I'm going to make a side note here. It is only used in the United States, not in science. But just so we know, for Fahrenheit, water is going to freeze at 32 degrees Fahrenheit and boil at 212 degrees Fahrenheit, again at sea level or under 1 atmosphere of pressure. So we will use Fahrenheit just to become familiar and notice the difference and changes, but we will not use Fahrenheit in our measurements. We'll typically measure in Celsius and then convert that over to Kelvin. So on that note here, we do need to go over some temperature conversions. And I know Fahrenheit's only used in the United States, but I want you to be able to know how to convert between all three of those different temperature units that I just went over. So the first temperature conversion is Celsius to Kelvin. And the formula for that is K for Kelvin equals degrees Celsius plus 273.15. And I want you to notice here that Kelvin, it's a capital K, and it does not have a degree sign. That's really important to note as we go forward. Now the next conversion is from Kelvin to Celsius. So the formula for that is degrees Celsius equals K for Kelvin minus 273.15. And that 273.15, in case you're wondering where that number comes from, it is absolute zero. So 0 Kelvin is when we reach that temperature called absolute zero, which we'll get into a little bit more detail with the kinetic molecular theory. Our third temperature conversion is going from Fahrenheit to Celsius. So on this, the degrees Celsius is equal 5/9 times the degree Fahrenheit minus 32. Now the last temperature conversion that we'll go over is going from degrees Celsius to Fahrenheit. And for that formula, the degrees Fahrenheit is equal to 9/5 the degrees Celsius temperature plus 32. Okay, so before we go on, I want to overview and go over some example problems of how to be able to utilize what we just talked about with those base units. So we'll start out here with naming these two things. The first thing that we want to name is what is something that equals 1 times 10 to the negative 9th grams. And so the way in which we find something like this is from our conversion sheet. So in our conversion sheet that I gave you in these notes, what we're going to do is we're going to find 1 times 10 to the negative unit, and then over there that says that is equal to a nano unit. So this right here, because it's 1 times 10 to the negative 9th of a gram, this is equal to a nanogram. Now we do the same thing for 1 times 10 to the negative 3rd meters. Again, we look at our sheet, we find 1 times 10 to the negative 3rd, and we look over here, this is the prefix milli. So 1 times 10 to the negative 3rd is a millimeter. Now down here, we want to know how many picometers are in 1 meter. So again, what we do first, almost the reverse process, we go down, we find pico, all right? Then we see here, the meaning of that is 1 times 10 to the negative 12th. So this means that we have 1 times 10 to the negative 12th meters equal to 1 picometer. Now this doesn't quite answer the question, and so what we need to do is this. We need to use this conversion and make a conversion factor. So what I'm going to do here, over here, I'm going to set up a conversion factor. So I am going to have 1 meter, and then down below, I always want to cross cancel my units. So I'm going to have m for meter, and then on top, I am going to put my unit, which is pm for picometer. Now we just use what we have here. So for every 1 times 10 to the negative 12th meters, we have 1 picometer. And so what we do here, all we need to do is we need to take 1 divided by 1 times 10 to the negative 12th, And we get 1 times 10 to the 12th PM in 1 meter. So 1 times 10 to the 12th PM equals 1 M for our meter. So that means there's a lot of picometers in 1 meter. And so we can do the same thing in this problem below. We want to know how many grams are in 4.22 milligrams. So almost like the reverse process. So the first thing again is we go and we find mg, which is the abbreviation for milli, and we see here that the meaning is 1 times 10 to the negative third. So that means there is 1 times 10 to the negative third little mg equal to 1 gram. We start out not with just 1, but with 4.22. So we go and we have 4.22 mg. Always put down what you have. And then we're going to do this. We are going to get rid of our particular unit, and we are going to do this. We have mg on the bottom, and we want to go to grams. And I have made a mistake here. No big deal. This 1 times 10 to the negative third. This 1 times 10 to the negative third should be g, and this 1 should be mg. And that will make a difference here as our calculation. So I just flipped those. I made a mistake. And so we have 1 times 10, still made the mistake. We have 1 associated with mg, and we have 1 times 10 to the negative 3 grams. So all we need to do here is we need to take 1 times 1 times 10 to the negative 3, and we end up with this value. Now, what I also have to do is I have to multiply it by 4.22. So what I should have done here is I should have put 4.22 times 1 times 10 to the negative third, and you get this value of 0.00422. Again, I made a little mistake here because I wrote down the conversion factor, but always take your time in that particular process. Our last problem that I want to do with our SI base units is convert 31 degrees Celsius to Kelvin and to degrees Fahrenheit. So first we'll convert to Kelvin. So what we need to do here is, if you look at our formula to go from degrees Celsius to Kelvin, we need to have our formula of K equals degrees Celsius plus 273.15. So what we do here, we insert K. We don't know that yet. Our degrees Celsius is 31 degrees Celsius plus 273.15. So when we do that, we end up with 31 plus 273.15, and that gets us a value of 304.15. Now, if we were rounding via significant digits, which I haven't taught yet, that would just round to 304. But if it makes you feel warm and fuzzy, we can write down all of this value because I have not taught you significant digits. Now, to go from degrees Celsius to Fahrenheit, what we have to do is we have to take 9/5 the value of our degrees Celsius and then add 32. So again, degrees Fahrenheit, we take 9/5 times our degrees Celsius temperature, which is 31 degrees. And then we add 32. So our degrees Fahrenheit, if we plug this into the calculator, I'm going to do it in 2 different steps here. So I have 9/5 times 31, which is our degrees Celsius. I press enter, and then I add 32. So our value for this becomes 87.8. Now again, if I was doing significant digits, this would round to 88 degrees Fahrenheit. But if it makes you feel warm and fuzzy, we can keep the degrees Fahrenheit at 87.8 degrees Fahrenheit. All right, so that is our SI base units. What we can do a little bit further is we can convert, or we can go into something known as SI derived units. So we'll transition here to our SI derived units, and an SI derived unit is obtained through using multiple of the 7 SI base units. So in chemistry, there's 2 really common SI derived units that we'll use very frequently. The first of which is volume, and this unit is derived by the SI unit of length that is cubed. So to help see that here, we can think of volume as taking the unit of length, which is meters, and cubing it. Let me put it in a mathematical concept for us. And so if you're thinking about this, think about a meter stick. We're taking a meter length times width times height. That unit is absolutely huge, and it's almost unrealistically large. And so what we have is some actual reasonable units that are applicable to us. The first reasonable unit is a cube centimeter. And so a cube centimeter is also equal to 1 milliliter, or 1 cube centimeter, or they commonly call this in medical terms a cc. Now another reasonable unit is a decimeter cubed, which is the equivalent to 1 liter. And it's also important to note here that the liter, the unit of a liter, is not the SI unit for volume. Again, the liter is not the SI unit for volume. Now, density is defined as mass divided by volume. And it's a lot easier to see this in a mathematical formula. So that mathematical formula is D for density equals M for mass over or divided by V for volume. And one thing to note here is that this property of density is temperature dependent. And so the unique thing about being temperature dependent, think about volume. What happens as you start to heat up water on the stove? Well, over time, it's going to start to evaporate, and so that means the volume of that liquid is going to slightly change, which is going to affect that particular density. Now, our units for density for things like liquids include either grams per centimeters cubed or grams per milliliter. Now, for gases, because those molecules are spread out a little further, usually the unit that we use is grams per liter. Now, because both volume and density involve the measurement of volume, I want you to be familiar with some of the common tools that we use in chemistry to measure that unit of volume. The first is a graduated cylinder. We can also use a syringe. A burette is another common measuring unit for volume. A pipette is yet another effective tool for measuring volume. And then we also use something known as a volumetric flask. Okay, so now that we know some of these derived units that we'll commonly use in the lab and in some calculations, I want to go over some example problems. So we'll shift here to our last page. And so for this, we start out with a real simple question here. We want to know which of those following below, A through C, represents a volume measurement. So we look at our first item here. We have 15 meters squared, 2.5 times 10 to the second meters cubed. and 5.77 liters per second. So remember, if you look back, volume, the unit for volume is units of length cubed. If you take a look, there is only one unit that says units of length cubed. And so this answer B would be the correct unit. And the reason that C is not the choice is because it's liters per second. So that's a rate that we don't want to add in that business there. So we'll move down here. We want to calculate the density of mercury if we have 1.00 times 10 to the second gram, and that is occupying a volume of 7.36 centimeters. So the first thing that we always need to do is write out our formula. So density equals M for mass divided by volume. Again, it says calculate the density, so our D for density is going to remain as our variable. Now M for mass, the unit for mass in this particular problem is 1.00 times 10 to the second grams, all divided by our volume, which our volume is 7.36 cubed centimeters. So what we do here, real simple, we plug this into our calculator. And so what we have here is 1.00 times 10 to the second, and notice how I put parentheses around my scientific notation. We divide that by 7.36, and let me zoom it in here. We press enter. Now we get this big long set of numbers. I'm going to teach you a little trick here. We had 3 significant digits, and I'll talk about that in the next lesson, but we need 3 total digits here in our calculation that we've obtained. So this would be 13.6 grams per centimeter, and that's centimeters cubed. Now if you look back on your sheet, the previous page of notes, this can be just as easily thought of as 13.6 grams per ml. Milliliters and cube centimeters can be used interchangeably. All right, our last problem here, another density problem. We want to calculate the volume of 65 grams of liquid methanol if the density is 0.791 grams per milliliter. So again, always start with your formula, and then we can just plug numbers in. So our D for density is given at 0.791 grams per milliliter. So this time we have 0.791 grams per milliliter. This is equal to our mass, which our mass is 65.0 grams, divided by our volume, or V. Now volume is what we want to calculate, so V would be on bottom, and now we have to do a little algebra. So to do this, we're going to pretend that these things are equivalent fractions. So all I'm going to do is put 0.791 over 1, and then what I'm going to do here, I am going to cross multiply. So I'm going to take 0.791 times our V for volume. And so when I do this, I get 0.791 grams per ml times our V equals 1 times 65, which is still just 65 grams. And so to get V by itself, I'm running out of room here, but to get V by itself, you need to divide each side by 0.791. Okay, so we take, again, 65 divided by 0.791, and we press enter. Now, we get, again, a long decimal. But notice here, there are 3 significant digits, and 3 significant digits here with 65. So that means our answer becomes 82.2 as our unit for volume. So V equals 82.2. And if you notice, if you divided this out, grams would cancel, and we would be left with ml for our volume. All right, so that concludes another episode of Science with Surbeck. As always, I hope you have enjoyed, and as always, subscribe.